Now, materials will be taken from this book. The green one you see at the top, textbook, Integrated Electronics, Analog and Digital Circuits and Systems, Jacob Millman and Christos Halkias. Millman Halkias books on yellow color book. Yellow pad, sometimes people are telling yellow pad or Bible of Electronics. It's a very famous book. Have you come across this book in your earlier course?
Yes, sir.
In your Principle of Electronics?
In first semester. Yes, sir.
In first semester. So, the same book. So, you were aware of it. So, many things will be known to you, I hope. So, things is going to be easy if you have followed that book earlier. I have not started recording, so let me do that. The main textbook will be Integrated Circuit Electronics by Millman Halkias. Other books you'll see sometimes very only few, maybe this digital principal electronics for ADC DAC, current mirror from somewhere. So little bit portion will be there, maybe 10% only. Otherwise, 90% things will be taken from your Integrated Electronics by Jacob Millman and Halkias. And in the first module, we have to go through these topics. A review of hybrid models of BJT. You are aware of BJT or not? You might have seen in the first semester itself. Simplified hybrid models of CE, CB, and CC configurations. CE, common emitter, common base, and common collector configurations. CE, amplifier with emitter resistance, emitter follower, high input resistance transistors, circuits, Darlington circuits, cascade amplifier of electronic device and circuits. You can get it from that book, Electronic Device Circuits by Millman Halkias. Then transistor power amplifiers, circuits and operations of class A, class B, class C. It can be seen nicely from Shedra Smith, 6th edition, and push-pull amplifier configuration. See, I have written the chapter number also, 8.3 of Millman Halkias, 8.13, 8.5, 8.14. These are meaning the hinting the chapter number. If you go inside the book, you'll see it is available there. Okay. Sometimes I have written some other book like Cascade Amplifier. I have written 11.17 of electronic device and circuits. That is different book. The mostly things is from integrated electronics, but this portion little bit is taken from electronic device and circuits by Millman Halkias again. Then transistor power amplifiers. This is taken from Shedra Smith, 6th edition. Okay, so mostly it is not out of book or material for material in not to don't here and there. If you have the book, then material is available to you. Okay, so I suggest take the book, either purchase or if you have some PDF copy, start using that. Okay, Busra?
Yes, sir.
first bring or take the book. It is very useful because most of things is available from that ALOFAD. See, in this course, at the beginning, I am showing you some theorem like, Norton and Thevenin theorem. These theorems you have studied in your earlier courses, possibly in network theory somewhere by electrical department or not. Tell me, Pratham.
Yes, sir.
So you are thorough about this. I hope I should not repeat anything. Are you remembering anything of that? Many networks, resistance based network you have come across and solved some. You have found the Thevenin voltage, Thevenin resistance, then Norton short circuit current, etc. You have solved the equations also. Simplified the network. Am I correct or not? Have you done,
Yes.
or should I
Yes.
repeat anything here? Should I repeat, or you can recollect and study yourself?
Sir, can you please briefly explain it again?
These are the theorems going to be used extensively in this analysis of the amplifiers based on BJT mainly, and of course a little bit on the MOSFET also. Okay, as you can see in the diagram itself, to find out the Thevenin resistance, what do you do? The network is given to you, the top figure. What you have to find out, Thevenin voltage or Thevenin resistance. It is what is the method? Suppose Thevenin voltage you want to find out. Remove the load. Remove the load, that is RL, the red resistance, and if you connect a voltmeter, then what you get is the Thevenin voltage. VTIs is a network of resistance along with some DC voltage. Keep the DC voltage intact. All the resistances is intact except the load resistance. You want to find out the voltage across the load resistance. You remove it, connect a emitter. What you get is the Thevenin voltage, VTIs. Now, if you want to find out the Thevenin resistance, what do you do? You remove the RL as you earlier you have done. Now, what you do is you remove the voltage source. Removing voltage source is nothing but shorting it. If you short it, voltage across the voltage source is zero. So, see that we have shorted with a wire at the bottom. Are you able to see? Are you able to see my? Here you have done, what you have done is you have shorted. You have put a wire here. So you have shorted. So if you measure, rather connect a avometer here, removing the load resistance. Okay. You have avometer, okay, which can measure voltage, current, and resistance. Then what you get is what? Resistance, Thevenin resistance. Okay. That is the way we, of course, if you analyze the circuit, you will see that your resistance 6 ohm and 3 ohm, 3 kilo ohm and 6 kilo ohm are in parallel. and that is in series with 4 kilo ohm, and finally you get RTA is equals to 6 kilo ohm. Okay, and voltage, if you want to calculate, what you with the avometer you can do it. Okay, connecting in this way, removing the load, but if you mentally calculate, what you get, we see that voltage across this resistance, 3 kilo ohm resistance, you have to find out, and it is a easy things. Okay, 72 volt is the voltage of the voltage source, and you can find out in this way, 3 into 3 by 6 plus 3. That is the way to find out. I think you are recollecting or not. VTAs and RTAs is understood from this diagram. Harsh Tripathi.
Yes, sir.
So it is so easy. Just for Thevenize a circuit, what you have to do is remove the load resistance, connect a avometer, you will get the Thevenin voltage. If you want to find out the resistance RTH, what you have to do is remove the load and short circuit the voltage source. I mean, put a short or wire across the voltage source. If there is a current source, then what you will do? You have to remove it. Means it is open circuited. Voltage source is short circuited, current source is open circuited. Then you can find out the resistance RTH. In case of Norton current, it is the same way. I Norton or Norton current equals to, again, R. It is a short is applied across the load. Whatever current is, that is R short circuit. Short circuit is a Norton resistance is RN. RT is same, open circuit. I mean, load you remove and measure the resistance. So that's the way. Somebody's mic is on. Put the mic off. Okay. Put the mic off so that noise doesn't come. See that somebody's mic is on. Put it up. So it is easy way to do it, and same thing you remember. The Norton current is in parallel with the Norton resistance, as you can see from here. See, same thing is a little elaborately said. If you want, I can continue. Otherwise, I will go to some other things. Yes, Pratham, should I continue further or it will be understood by yourself? What is the Thevenin theorem and Norton theorem? Bushra, Pratham, Harsh.
Yes, sir. It's understood.
Understood? Okay.
Yes, sir.
If not, please go through. This will be used in future. In that time, I'll not discuss anything. I'll say that if you Thevenize, then you will get this thing. Or if you Nortonize, then you will get this circuit. That's all will be MOSFET based or BJT based small signal model. Small signal model of the BJT, and in that Thevenin theorem will be applied or Norton theorem will be applied. Okay. Similarly, other theorem will also come. So in that time, you may have to refresh yourself. So this, if you are taking the screenshot, you read it. It is a very simplified way I have put it. Okay. I'm just keeping these slides because it is known to you how not nice is done. You put a shot across the load to find out the ISC, short circuit current, which goes in parallel with the RTH or RN. RN or RTH is same. Okay, so it will go in this. And in case of Thevenin, that VTH goes in series. VTH goes in series with, say, like this. It is RTH. Okay, there is a voltage VTH. So this way, simplified. Big network will be simplified in this way. In this case, it is in series. In this case, the current is in parallel. Going further and skipping all those things, I am some corollaries based on this theorem, Norton theorem and Thevenin theorem. If V represents the open circuit voltage, open circuit means your load is disconnected, and I is the short circuit current, as in the case of Norton current, and Z is the impedance, or Y is the admittance in a network. Then we can write Z equals to V by I, or I equals to V by Z, which is equals to V into Y, or V equals to IZ, which is equals to I by Y. These are silly things for you, I hope. Very simple things. Yes or no?
Yes, sir.
So we'll start with these silly things, but what is going to come in future is little tough. Okay, don't be carried away with this kind of things. These are fundamentals, so just you refresh your mind with these simple things. The left hand side diagram is the Thevenin equivalent, and this is not an equivalent. Now you might have studied earlier circuit here in figure 5-3A is a common base configuration of BJT. BJT means bipolar junction transistor. And why it is common base? Why it is called common base? See, the base terminal of the, this is base, this is emitter, this is collector. So as a PNP transistor, as you can see, the arrow is pointing towards base. The conventional flow of current direction, you can say. So in this, base is common to input as well as output. Okay, input will be applied at this point. Okay, input signal may be applied here. Okay, very small, in millivolt, for example, which has to be amplified by this amplifier, right? And output will be taken from here, this side, across the RL. You see that? But applying input to the amplifier and taking output from the amplifier, base terminal is common. So it is called common base configuration. Is it understood?
Yes, sir.
Why it is called common base? I hope it is understood. Another configuration is common emitter, which is mostly used. We'll study why it is used, what are the characteristics in future. But this configuration, as you see, emitter is common to the input side. Input, this side is your input, and this side RL, load resistance is that right side connected to the collector. So output will be taken across this point. So it is also, you see that emitter is common for both input as well as output. So it is called common emitter configuration. Okay. Another topology or configuration is common collector configuration. As you can see, this circuit is common collector. Can you say why, how it is common collector? How collector is common? It was understood in case of C amplifier and CB amplifier that we are understanding this point, base or emitter are common. But here, how it is common collector? How collector node, is common to input as well as output. Who can say? Tripathi?
Sir, don't.
Don't know. Pratham?
Sir, can't say.
Bushra?
Sir, I'm thinking,
Aman?
analyzing.
Aman?
Sir, I don't know.
Okay. But you have studied, I hope. These configurations, the three configurations I am talking about, have you heard these configurations earlier? Tell me.
Yes, sir.
Yes, no?
sir.
All of you heard, but never asked, why it is common collector? Or it is not told to you. There must be some reason why it is called common collector, why it is called common base, why it is called common emitter. Not known. Okay. See, when you perform the AC analysis of a circuit, what is done, the DC source is grounded. Okay, DC source is grounded. And simply, if I keep this circuit and apply the same thing, then it is nothing but I have to ground this point. Okay, it is grounded. Once it is grounded, you'll see that the output is taken from emitter to ground. Output is taken from emitter across the RL, which is connected to the emitter, and that is the output is taken between emitter to ground. Input is applied between base to ground. So this since collector is grounded, you see that collector is common to input as well as output. Yes, Harsh.
Yes, sir.
So now you are not asking why the DC source has to be grounded for AC analysis. Why you are not asking that? I said that DC sources has to be grounded. All the DC source voltage. If it is voltage source, it has to be shorted to ground. If it is a current source, it has to be opened. Zero current means what? through a current source, current is zero. To make current zero of a current source, what you have to do? You have to make the impedance infinite. And infinite you can make if you open it. Right? Suppose you have a current source, suppose, and you want that current should be zero. What you can do? You just open it. You just remove it. Remove this, and the resistance here is what then? Infinite or not? If it is infinite, no
Yes,
current.
sir.
So for the case of current source, it has to be removed or opened. If it is a voltage source, suppose you have a battery, okay. If it is a voltage source, you have to make this voltage source zero. I mean, there should not be voltage across this terminal A and B. What you can do to do that? How you are going to make this voltage zero? Simple. You connect a wire across this A and B. You are shorting, okay, or shorting to ground. Suppose this side is ground, so you are shorting to ground. Are you getting my point? For voltage source, it is grounded. For current source, it is opened to make the
Yes, sir.
voltage and current zero. Okay. Now question is why at all has to be done for AC analysis. Remember this voltage sources you are seeing here and there. These are bias voltage and currents. Okay. Bias. No, bias means what? For a PNP or NPN, say, let me take it. It is a PNP MOSFETs. I mean BJTs. These two are the PNP BJTs. Let me just draw the structure of NP NVJT. So you have come across that it has to be biased for its operation, proper operation. Proper biasing is required. So how you bias it? Proper biasing means what? To make it function as an amplifier, how you are going to bias? Tell me. Forget about this circuit here. Just the things I have drawn here. NPN. How are you going to bias? Show that. Okay, verbally you say. Verbally you say. Terminals are E, B, and C. How are you going to bias so that it is properly biased and it can work as an amplifier, for example? Tell me. In one semester you have studied mainly this kind of things. Tell.
Emitter base will be forward bias and base collector will be reverse bias.
Base emitter junction is to be forward biased and base collector junction is to be reverse biased for its proper operation. Very good. Who is that boy? Himanshu. Good. So you are recollecting some certain things. So for biasing only you are applying this VCC here and there. Understood? Its purpose is to bias in such a way that base emitter is forward biased and base collector is reverse biased. That's what your idea. Connecting this DC sources. Once the BJT is biased in this way, it can work as an amplifier. Then you can apply small signal across the input. Okay, across the input, very small signal. Okay, say 1 millivolt or 2 millivolt source that may be generated by a what is called microphone. We are speaking in microphone, that may be generated by microphone. Okay, or an antenna or any transducer or sensor that sensed or picked up voltage signal is so small in the microphone or so that it is not audible. Say directly, if you try to connect this microphone output, which is a very small voltage, if you connect the output of a microphone to a speaker, can you listen anything without any amplifier?
No, sir.
Obviously no. So you need an amplifier which will be taking this small signal generated by this microphone and amplify it to a level which is suitable for driving a speaker. That is the purpose of amplifier. It will take small weak signal, amplify it to a certain level, and it can drive some load resistance or say speaker resistance. Okay. So what I was telling is these voltage, DC voltage are just to bias it. Without this kind of DC biasing, your amplifier is not going to work. You have already studied that base emitter junction should be forward biased and base collector junction should be reverse biased. Then only it is going to work. So VCCs are connected for that purpose only. Now let me go ahead a bit. Now you have not asked, but let me ask, why coupling capacitors are open for DC analysis and shorted for AC analysis? That's the first question. Second question is, why DC voltage source is grounded for AC analysis? Just now I was talking about that. Tell me any answer to these questions. You have done one semester course earlier for doing this, and you have done, I hope you all have done it. Coupling capacitor, you know. What is coupling capacitor? Yes or no? Do you know the coupling capacitor or not? Not remembering? Coupling capacitor is what? Suppose you have
Sir,
tell
sir, which allows to pass only AC signals from. It is like a connecting bridge between two circuits which allow to pass only AC signals and not the DC one.
suppose this is a this is an amplifier. See, amplifier basically. And for biasing the base and collector, you have connected R1 or 2 voltage divider. Some voltage will be here, and you have connected RD so that collector is also biased properly. I mean, base emitter is forward biased and base collector is reverse biased. That way you have done, and it is an amplifier. Output is taken from here. Okay. The VM here is very small, maybe 1 millivolt, and it could give say 10 times, so 10 millivolt it could give after amplification. Okay. Input was say very small like this, and it could amplify and say it is like this. Amplified version. It is say amplified version, or let me is inverting. If it is inverting, then it will start like this. Okay. Suppose this is not enough. This 10 millivolt is not enough to drive a speaker. You need further amplification. Means another stage is required. Another stage means again, once again, you have another RD, say RD2. You have a BZT based amplifier, and you have voltage divider here. I am same amplifier I am replicating, and VCC here. Okay, another stage to further amplify, okay, so that you get a very large voltage, output voltage. Okay, so can you directly connect this output? You want to connect directly. Is it possible to connect like this? There is some problem. So what you, because this direct connection may disturb the biasing. Suppose here you wanted everywhere, here the voltage you want say 1 volt. Exactly 1 volt you want. Suppose it is 5 volts. Okay. Exactly 1 volt you want. But if you connect here, you see that it is amplified and some voltage is here. I mean, some voltage dropped here and some is available here, and that is going to be connected here. So bias voltage, which should be 1 volt, it is getting disturbed by this connection. So you cannot connect directly like this. Of course, if you want to connect, then you have to ensure that this voltage, output voltage of the first amplifier is not disturbing this one, this voltage of the second stage. Then we can do. Otherwise, best way to connect is connect with a coupling capacitor. Coupling capacitor put DC is isolated. Okay, DC is isolated. This DC over here I'm sorry. I wanted to hide this. This DC should be isolated. I mean, this point should be isolated from this point. Voltage here and there are different for properly biasing. Properly biasing means, remember that base emitter forward bias and base collector reverse bias. That may be distant, may not be possible if directly connect sometimes. So in that case, connect this one. So this is what and the coupling capacitor, coupling between two amplifier stages. Output of one connected to the input of the next stage. Could you understand what is coupling capacitor? Harsh Tripathi?
Yes, sir. But sir, why it is opened and shorted?
That we are coming here. First of all, you are not knowing what is coupling capacitor, so I started talking about coupling capacitor. Is it understood, Bushra, what is coupling capacitor?
Yes, sir.
Once you are using a coupling capacitor, you are safe. Biasing of the amplifiers are not getting disturbed. Am I clear, Pratham?
Yes, sir. Clear.
Now point is why it is to be opened or shorted for AC analysis. I should not say much about this as read it. Okay, read it. You will understand and tell me whether you are understanding or not. First paragraph you understand. Is it understandable? First paragraph, could you read? Yes, tell. You could understand or not? First one. First question is answered.
Yes, sir.
Is it was known to you or not? Thing was known to you that at very low frequency, a capacitance offer a very high resistance. Zero frequency means infinite. It is known to you or not? Tell me.
Yes, sir. It was known.
It was known because your xc equals to 1 upon twice pi fc. Okay. If this is 0, if c equals to 0, then it is infinite. That was known to you. And that's the reason. Well, AC, I mean, for AC signal, it is short. If it is high frequency, if it is high frequency, very high frequency, then X is 0 almost. Okay. So, regarding the second questions, why DC voltage source is grounded for AC analysis? Is it clear? See that a DC voltage source has constant voltage across it. Therefore, any AC current through it cannot produce an AC voltage across it. If no AC voltage can exist, the DC voltage source is equivalent to an AC short or AC ground. Mean to say, DC voltage, say 12 volt or 5 volt or 1.5 volt. One pencil cell is 1.5. If you across it, if you apply some AC voltage, its voltage is not going to vary. No change in voltage, no change. You can say no change or zero change. Zero change. So we say is a at 0. So for DC is concerned, it is at 0 potential for a AC signal. For a AC signal, DC voltage is a 0. No change occurs. Change is required for AC. Change is required. Change is required. Maybe in this way, a sinusoidal or so. No change, so 0 change. 0. So for AC signal is concerned, DC source is 0 or at AC ground or AC short. Could you understand? We'll be using these concepts, all these concepts in future for our analysis of circuits. Remember that. Now, after this, immediately you have class, or should I stop here?
Sir, we have class.
Okay, then I'll stop here and continue from here in the next class. These all are fundamental things what I am going to talk about. but these concepts will be very much useful in analysis of this subject, amplifiers, etc. See, we have not yet started the things. We are just preparing our background or reminding you what you have to study. Is it clear, Pratham? I
Yes,
can
sir.
see
It's clear.
56 students are there. I don't know why others are not there. Once again, I will take the attendance if possible. It doesn't take more than once. Okay. I hope in the next class, full 64 students will be there. 10 students are missing or 8 students are missing. It is not good things because some things
Sir,
yes, Amir, tell.
sir, by mistake I left the previous team, sir. Can you add me please once again?
What? Tell
Sir,
me.
I left the previous DSD team, sir.
Oh,
So can you add me once again, sir?
see, you send your email address through email,
Okay, sir.
BIT email address. Okay.
Yes, sir. Thank you, sir.
And if anybody of your kind, please WhatsApp and tell me to add. Otherwise, you may not be able to join. But how you have joined this team? By
Sir, sir, link, sir. Through link.
through link. Somebody has sent you the link.
Yes, sir.
Okay. If anybody is having this problem, please tell me so that I can add. Okay. So our class tomorrow at 10:15. Okay. We'll continue. Tell all the students who have not joined today should join here because something is missing. I mean, class is missed means you are missing something, and questions will be from beginning itself. Fundamentals also will be covered. Okay, let me say bye today.